Hello, everyone. My name is Kusha Raisi. I'm a second-year doctoral student at the Structural Engineering Research Group. My advisor is Professor Yu, and our group is located at UMass Lowell in the Civil and Environmental Engineering Department. Today, I'll present to you what is a very small summary, kind of an overview mostly, of what I've been doing regarding my project, which is titled Corrosion-Induced Crack Detection of Reinforced Concrete Structures using a 1.6 gigahertz GPR device. As for an introduction, the research problem that we're trying to solve is the structural assessment of aging concrete highway bridges in New England. And chloride-induced corrosion specifically, which leads to cracks, kind of a cause and effect thing, is very prevalent in New England. And the big question that I want to answer is how to characterize, quantify after detection, how to do this for the crack parameters, most importantly, crack depth, and subsequently other parameters that stem from this big question, this big problem that we're trying to solve, which I will address in the following sections of this poster. And as you can see in figure 1, corrosion happens in 4 qualitative stages. Of course, we have a variable called degree of corrosion that we can more accurately characterize the advancement of corrosion. But conceptually, we can put it in 4 categories. The first one is stage 1, which we call the intact, so to speak. But it's not completely intact, as this is a stage that we call hydraulically permeable, as the hypothesis is that the pores are interconnected and there is a pathway for moisture to get in, for chloride ions to move freely and have this electrochemical process. As for stage 2, we commonly call it depassivation stage because the coating around the rebar cover, around the rebar, that's protects the rebar from corrosion or anything. So this passive shield, this shield is dissolved. It gets infiltrated, and the rebar is suddenly naked and exposed, and that's when everything gets triggered, and the whole process starts. As you can see in stage 2, we can see cracks, and but we cannot see anything on the surface. So this stage is what brings out the most important thing about assessment with non-destructive methods. So we can detect this problem before it reaches stage 3 and stage 4. And again, the process, how it works is that when rust is accumulated, when rust is going to get created by this triangle of moisture and oxygen and chloride ions that get in from, for example, salts. So this triangle, in order to satisfy this, when rust is formed, is typically around 6% more expansive than iron itself. Therefore, it causes stress, and the stress in concrete is a problem, because that stress is going to distort the balance of stress distribution in our concrete matrix or medium. And as you know, because of the interfacial transition zone, or the ITZ, the concrete is very weak in terms of tension. Therefore, this stress redistribution causes concrete cracking. And it starts from the rebar, around the rebar, and gradually comes to the top, where we can see it in stage 3. And quite frankly, stage 3 is where we already can see the crack, so we can attribute it to this. We want to sort of see this before stage 2 happens. But in order to do that, we have to work with stage 3, because in order to use the NDT device to argue your case, to start doing research on it, to get us to a physical meaning quantified by math or other methods, we have to have some evidence. So the evidence is the crack. Essentially, the difference between these two is the degree of corrosion. But the main difference is we can see a crack on the surface. So that's where we'll start. And then it's the final stage that we can be so confident that we can find it in stage 2. That would be great. And as for stage 4, well, we call it spalling. As you can see, the rebar is exposed, and well, there's not much we can do at this stage. And in figure 1B, you can see the GPR device. Also, figure 1C, there is another GPR device for pavement analysis. So they come in all sorts of antenna models and more importantly, frequencies, which when we have higher frequency, we have lower penetration depth, but we have more resolution. And of course, different applications need different devices. And in this figure, you can see the electrochemical process that happens when corrosion is introduced, when corrosion is initiated. And in this image, we can see an A-scan image, which is one signal in time, a one-dimensional signal in time. And the combination of these one-dimensional signals will eventually give us a heat map image representing the amplitudes in the cross range and in the range direction. So, for example, if we cut the middle of the rebar here, which we call the apex of this hyperbolic pattern that represents the rebar in our B-scan image, we can see the peak of it. And also we can see the direct coupling signal, which represents the boundary, the interface between air and the B-scan image, and sorry, the concrete. And as for what we started to do to sort of answer this, advance toward answering this big question about this project, is starting with laboratory samples. So we casted 10 laboratory concrete specimens. We call them CN specimens, 12 by 12 by 2 inches cube. And with the same water to cement ratio, aggregate ratio, and same materials, everything controlled. And we used styrofoam to implement cracks, rectangular cracks, so to speak, cross-sectional cracks of various sizes. So we can try to see how the scattering pattern affects our GPR B-scan image and how we can quantify it from there. And of course, laboratory work is only half the job, so field work has to be done. Therefore, simultaneously, we always try to scout and find different places to scan. And as you can see in figure 2B, we have a portion of a parking lot wall, concrete wall, located at UMass Lowell's North Campus garage. And another thing that we did is we casted 3 12 by 12 by 5 inch specimens, this time reinforced at their center with a number 6 rebar period. And we used the impressed current technique, which is an accelerated corrosion test method to accelerate corrosion and facilitate reaching the point that we want. So we achieved stage 2, corrosion, no crack, and stage 3, corrosion and crack. And we had one intact specimen. So we started scanning those as well. And the results, as you can see here in figure 3C, this is the original V-scan image. As you can see, these parts are what we call the corner scattering effect, because some parts of the EM waves get scattered into the air and don't directly enter the medium. And you can see the 3 bars depicted as hyperbolas. And you can see the concrete and the wood plank underneath it, their interface. So we started analyzing it in time using A-scan signals. So we want to see the effect of radar parameters and how they can affect corrosion and the combination of these actions, corrosion and cracking. And as we know that the top or the apex of the hyperbola represents the top of the rebar. As the reason that we see this as a hyperbola is that as we roll the GPR, and it starts sending pulses of transient signals, the travel times are different. And as the GPR gets closer to the target, the travel time gets smaller and smaller, and that's why you see it as a hyperbola, because the images are not superimposed, in contrast to another radar that we have, synthetic aperture radar. So if we cut the apexes here, find the maximum amplitudes, and you can see here that the maximum amplitude reduces at the apex hyperbola cut, cross-range cut that represents this A-scan in time. That amplitude reduces as corrosion progresses. Not only the amplitude is reduced, as you can see here, S1, S2, and S3 represent stage 1, stage 2, and stage 3. Also, the travel return time of these signals are also reduced. So these are two things we found out from this. And again, doing a Fourier transform and transforming and seeing this A-scan signal in frequency domain, of course, we still see amplitude reduction, but again, we also see frequency reduction. Now, the important question to answer here is how we can distinguish crack plus corrosion from crack and from only crack, or actually more realistically, only corrosion, because that has precedent over the other. And as for the CN specimens, the artificial cracked specimens with 2 inches depth, we can see the GPR images. We actually put aluminum foil to act as a beacon or perfect electric conductor with a high reflection, so we can see the bottom, the interface between the bottom of the specimen and the floor, because the specimen is not very thick, and it might be hard to find the boundaries because the direct coupling signal might disturb the first 1.5 inches of our image, which is a prevalent problem in GPR images and needs to be addressed. So as you can see, these are the V-scan images. You can see the boundaries of the beacon. And at the bottom, we have the feature extracted image of them. So imagine that this image is reduced to only the local extrema. So what does that mean? Local extrema means local minima and local maxima, because a signal, positive signal, is followed by a negative signal. So these strips of signals which stem from these A scans here, they're all reduced by a single point here, 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 and here, across all the cross-range axes. And that gives us a reduced image that has less features, less clutter, that can help us in assessing. As you can see, we can see these bumps or anomalies. We call them hyperbolic anomalies for the cracks. But unfortunately, like rebars, we cannot see them as nicely. And sometimes the pattern may not completely resemble a hyperbola. And so doing this ACT experiment and assessing it with GPR, we found out, for conclusion of figure 3, that steel rebar corrosion results in reduced GPR amplitude, reduced travel time, reduced frequency. And the reason for that is due to the growth of small fissures around the cover. So one thing is material, surface roughness of the corroded rebars due to rust formation. And our findings are in good agreement with other researchers, especially some of the older researchers who were pioneering in this research many years ago. And back to our cracked specimens. So we did actually what happens in the field: corrosion, cause and effect, which is crack. So we did this experiment. But it is also important to just start with cracks that might not be exactly realistic, like the cracks that we naturally created here, which is has a highly nonlinear geometry. So we reduced it again, just like this feature extraction, reduced it again to simple rectangular cross sections, because we want to start with something simple, no rebar, nothing, and controlled cracks. So we have all the information, all the dimensions, and we control it, and we can start quantifying from there and then move up, up, up. First here, and then going back to going to the advanced stage of implementing whatever quantification that we have created for actual structures, which is what makes it fruitful in the end. So back to this one. As you can see that I truncated, I made it larger, and I zoomed in the direct coupling part, which is like this part, positive, negative, positive, negative. Direct coupling signal, because that represents what's happening in the surface. And as you can see that we can see these hyperbolas, even without removing or trying background removal processes to remove these direct coupling signals, we can clearly see it, because always the first thing in GPR imaging is overview of visual analysis before moving to anything else. So visually, we can see them. We can see it, these hyperbolic patterns. It's important to look at both positive and negative signals. As you can see here, the negative signal has a better representation than the positive one here. But in some cases, all the signals, all the mappings give us very good results. Now, I forgot to mention one thing. I explained that in this feature extraction, reduce the signals to only their extreme values, which is minimum or maximum, which their peaks or valleys, so to speak. But we have also mapped the edge boundaries, the top boundary edge here of the positive one, and the bottom boundary or edge, and the same for the negative scan. Because of what I mentioned earlier, that cracks are unpredictable, we may see them as hyperbolas, we may not see them. Also, we don't know their depth and how it goes, extremely nonlinear geometry. Therefore, we implemented 5 different mappings so we can work them together and have more resources or variables to try to predict the possibility of a crack, and then start quantifying it by comparing physical parameters with the radar image variables. And we can detect the cracks in all the 4 specimens here. These are the 4 specimens that we have here, the ones here, and each of them have 2 cracks, and we can clearly visually see them. And by mapping them, we can see their hyperbolic patterns, which can be quantified mathematically. And in figure 5b, we have the 3 B scan images, scan 1, 2, and 3, 1, 2, and 3, conducted on the UML parking lot that I mentioned earlier in figure 2b. And as you can see, we have 2 cracks here, approximately from 9.5 inches, and 10 inches. And we can approximately see them in the same places in the cross-range axis. But it's worth to note that GPR is not laser, so it's not completely precise, and the GPR signals reflected are affected by a lot of things, which some have mentioned earlier. And even in 3 images of the same crack, only a few inches down, we can see that they're completely different from each other. For example, in the positive signal, the 3 mappings conducted for the positive signal, you can clearly see the 2 cracks in this image for scan 1. You cannot see the crack here, you can see it here, you can see it here, you can vaguely see it here. Again, here, the positive signal does not give us anything meaningful at all. So back to what I argued earlier, it's good to work with more than a few parameters so they can fill in each other's shortcomings, and maybe then we can put it together and find the best solution for this. So these are the problems. The big picture is the corrosion detection and subsequently crack geometry quantification, inverse problem, bringing it to the physical meaning, that is what the question wants to answer. But as you can see, there are many, many obstacles regarding this, which makes it a very, very exciting research to conduct. And this is what we do. So in the future, our goal is to, first of all, try to separate the corrosion action from combination of corrosion and crack, start attributing physical parameters to their signal parameters, whether it be A-scan signals in time domain, like here, or spatial mappings in the cross-range and range domains for signal edges, boundaries, or local extreme. So two completely separate methods, but they stem from each other. As for findings and conclusion, we can put it in 4 bullet points for now. One is that GPR can detect corrosion. We saw it. Many other researchers have seen it. It's old news. We know that it can. And corrosion-induced cover cracking, what do I mean by that? As you can see here, we can also qualitatively see, because it's so significant that we can actually see it. Even with the chosen color map that we have here, we can see the effect of corrosion here, cracking, and also cracking here. And I also suspect that there might be crack in here, micro cracks that we cannot see, but we can see it with the GPR. And comparing the combination of these two is actually a very interesting question. And the second one is that EM waves are sensitive to the medium, that is, the concrete dielectric properties. We neglect magnetic properties since we work with paramagnetic and non-magnetic materials in civil engineering. So it's just electrical dielectric properties. And environmental noise, which is highly susceptible to where you are, how many devices are operating, frequency you're using. And also, EM waves are heavily influenced by changes in moisture, which makes post-processing analysis quite challenging. Imagine you're in the field and you want to quantify a crack. You take images of something, you've solved all the problems. Tomorrow it's raining. The moisture content of today is not going to be same with tomorrow. And that impact is so influential on GPR that is mentioned almost everywhere. And that's always a problem. But that can be a good thing and a bad thing, obviously. And GPR can also be used as a supplementary NDT method or device for verification of the ones that are already very well established and reputable and accepted by everybody, such as half-cell potential and ultrasonic pulse velocity for crack detection, void detection, and HCP for corrosion, probability of corrosion ongoing, and while offering more resolution and fewer constraints in field implementation. As you know, for HCP, we have to, it's very sensitive to moisture. If the specimen is very dry, it's a wall, you have to dampen it with water. If it's your specimen, you have to dampen it, maybe sometimes even submerge it if needed. And that can actually mess with a lot of things. Like if you do that with these 3 specimens, our amplitude, our time, everything, because the dielectric properties get changed, the index of refraction, N, gets changed. Therefore, that's a very, very big problem. So we do not have that problem with GPR. We do not need to actually change or alter the moisture content or other properties of what we want to scan, even though it's called non-destructive, which is half destructive, because we need exposed rebar end. So that's the problem with HCP. And for robustness of GPR, one of the good characteristics about it, is that we can control the frequency and other radar parameters, such as polarization and cross-section, the antenna, to control the resolution and penetration depth. But there's a trade-off, as I said, less depth, more resolution, more noise susceptibility, more clutter. And it makes it a versatile tool, actually. It's pretty cool that it has all these options for structural host monitoring problem in civil engineering, such as transportation infrastructure like concrete bridges, which we are very interested in. I hope this research was interesting. Thank you very much for listening, and have a good day.